and welcome to our webinar, Mineralization, How to Trap CO₂ into Useful Rocks. Just have a little issue. Yep. So just that you know, this workshop is being recorded. You should be able to get at least some of the presentation after the workshop, and you are more than welcome to ask your question in the Q&A box. And the question, or at least all the questions we can address, will be addressed in a Q&A session at the end of the presentation. So I'm Celia Sapa, I'm the climate expert and head of communications at CO₂ Value Europe, and I'm now giving you a very brief introduction for this workshop. So who are we at CO₂ Value Europe? We are the organization that CCU means carbon capture and utilization. We also call it CO₂ recycling or CO₂ valorization or CO₂ utilization. And our role is to bring together partners from the whole value chain of CCU. So upstream, you have the CO₂ emitters, the renewable energy providers, hydrogen providers, raw material providers. In the center, we have the technology of conversion, so how to transform CO₂ into useful products. And we are focusing on three routes: the CO₂ to chemicals, the CO₂ to synthetic fuels, and the CO₂ to building materials. And downstream, we have all the infrastructure, the distribution, and the refining of the products. So in our consortium, we have members from multinational companies, SMEs, regional clusters, and also research institutions and universities. Today, we are going to focus on the route of CO₂ to building materials. So how it works, very briefly, because people will discuss about it later. So when we have CO₂ emitted from a point source, we can mineralize the CO₂ into building material to sequester it. But we can also take the CO₂ directly from the air and also mineralize it in bricks, for example. And that's what's going to be discussed today. So the mineralization process will be discussed, so I'm not going to explain it in detail now, but the important message to already have in your head is that mineralization allows to sequester permanently CO₂ in building material. So here is the agenda. So we are going to start with a discussion on the technical developments in CO₂ mineralization, and several of our members are going to talk now. First, Carbonate System, then our members from Vito and Orbix, and then Mitsubishi Corporation. And then Professor André Bardot is going to discuss the role of CO₂ mineralization in the climate change mitigation context with a life cycle assessment perspective. And then Stefan Gillis from our team is going to discuss the policy developments and framework for CO₂ mineralization. And we will close the session with a Q&A. So now I will give the word to Paola Carey, for the technical director of Carbonate Systems in the UK. Paola, please, can you share your screen?
Thank you very much, and thank you very much for the opportunity to talk about our recent activity in Carbonate Systems. Particularly what we've been doing recently is the direct flue gas capture of CO₂ into our process. So what I want to do is quickly give you a background to Carbonate Systems and then talk about this recent development. So the development of the company, we're a classic spin-out from the University of Greenwich, and it's quite a long time ago now since we first established the company. But our main work started in around 2010, when we established a sister company to commercialize the technology we'd been working on for 15 or so years within the university. And in 2012, we commissioned the first accelerated carbonation plant, treating around 30,000 tons of air pollution control residues. By 2016, there were two plants commissioned and a third on the way. So we believe that we've reached TRL 9 in the carbonation and treatment of air pollution control residues from energy from waste plants. In 2016, the main directors of the sister company returned to the core company Carbonate Systems to take the technology to other waste streams and internationally. And our main development started in 2018, when we developed what we call a CO₂ container, or however you want to pronounce that, that lettering. And we started pilot projects and demonstration projects through to 2019, when we secured some funding and allowed us to develop the container further, so that we signed our first global license and development and deployment of the first commercial CO₂ container with the VCAT Cement Group this year. We've also deployed a container system with AVR at an EFW in the Netherlands. And as you can see, we're building a global presence by working principally in Singapore, but also with other multinational companies. So the carbonate system solution, particularly our containerized system, I should emphasize that the 3 commercial plants in the UK use pure CO₂ that comes to them in a tanker. And because of that, there's a cost to the CO₂. In the UK, famously during the World Cup, some time ago now, there was a shortage of CO₂, and that's a regular occurrence if sources of CO₂ are under maintenance. So principally the CO₂ comes from fertilizer production, and as well as the cost, there is the shortage. So that's why we decided to move to flue gas capture directly, because it removes that uncertainty within our process. So the idea is that you have a containerized system that can be deployed to your source of CO₂. That might be a cement company, a steel works, or a EFW, or similar industry that's producing thermal residues. So you deploy your containerized system, which will capture the flue gas directly from the plant and treat the residues that plant is producing, thereby diverting those materials from landfill. And our process permanently captures the CO₂ in the mineralization step, so forming stable carbonates, by reacting the calcium and magnesium salts that are in those waste streams. And through the engineering within our system, we can produce, generally we're producing an aggregate, a lightweight aggregate, but we can also produce molded products. And obviously they're of benefit to the construction industry because they're carbon negative. They have more CO₂ captured in them than there are used in the process. And they can be used as a replacement for natural aggregates. One of the benefits of doing it this way is there's no requirement for the expensive purification of the CO₂. And we've achieved this with concentrations of CO₂ down to around 20% by volume of the flue gas. So that's the typical concentrations in these sorts of industries. So just looking at the potential for our technology, if you look at the range of waste that we've been looking at, there's the air pollution control residues from energy from waste. This is where the lime is injected into the flue gas to take out the contaminants, particularly the chlorides and sulfates in the residues. So we're also looking at fly ashes, where that's not necessarily does not necessarily have the lime injected, but they still have calcium silicates. Incinerator bottom ashes, so the bit that drops out the bottom of the grate, and then steel slags. And one of our main emphasis at the moment is the cement kiln dust or cement bypass dust from the cement industry. And you can see that you can take up a substantial amount of CO₂ in these different residues. Generally speaking, air pollution control residues, particularly nowadays, the way the lime is recirculated, the amount of reactivity has dropped somewhat. So we talk more about 5% for air pollution control residues. Whoops, sorry about that. Oops, can't get to the next slide. Oop. That's trouble with using a Mac. Let's try this one, that's better. So if we look at the volumes of those residues around the world, and particularly in Europe, this data is a little bit out of date now. It was based on the 2016 Eurostat data and various databases for the global volumes. But you can see that there are significant volumes of these waste streams around the world, and they have significant disposal costs. If you take just the European market, you can see that if we were to access all the waste that are generated, you've got a 12 million pound market, and also the potential to capture over 28 million tons of CO₂. If you look at these waste streams, a lot of them have other uses. So particularly in the steel industry, it's not as simple as it shows there with the market size. Not all steel slags are reactive to CO₂, and they can take up various different amounts of CO₂. The best ones are the stainless steel slags, and also those slags have got other uses, so they don't have the big disposal costs. A lot of paper ashes, for example, are already spread to land. But what we're watching out for is changing legislation, which actually makes it more difficult to dispose of these materials and reuse them. So there's a real opportunity to look at carbonation of these residues as a solution to some real problematic waste streams. So one of the big drivers to our business is the landfill tax. And this graph, and I'm sorry that some of the spots are on the lettering is a bit small, but it shows you the variation in costs of disposal across Europe, and plotted against the amount of residues that are available. So Germany stands out markedly over here, with a large amount of potential for treatment of residues and also high disposal costs. But there are a whole suite of European countries where really the economics of our process are probably not very favourable. So we've been concentrating on these markets over the last few years, and also looking at North America and Canada in particular. So the benefits of the technology, other than the safe and permanent capture of CO₂, which is what we're all talking about here, is that we are avoiding the landfill costs. And at the end of the process, we have a manufactured product with a value. So you get value at both ends of the commercial train. We're looking at typical treatment costs of between £25 and £30 a tonne of residue treated, and probably value of the product similar to that of natural aggregate in the order of €10 a tonne. But as I showed, the landfill value saving, we're talking about an average of €120 a tonne. So we progressed to direct flue gas capture, and our first demonstration of that was done with CRH at a CRH cement works in Ontario, and I can't pronounce the name of the cement plant, but it was near Toronto. And that was funded by the Ontario Solutions 2030 Challenge, which was a prize that was awarded in 2018 for a variety of CO₂ management companies. But you can see here clearly on the image on the right, there are two pipes coming into our containerized system. And this is a very straightforward way in which we are bypassing the flue stack. So the horizontal pipe there you see is the flue stack for the cement works. We take two pipes out of that, or stabbings within the gas pipe, and pass the CO2 directly through our containerized system. So the CO2 is stripped out of the gas, or some of the CO2 is stripped out of the gas, and any remaining flue gas is redirected into the flue stack, so that there are no emissions. So here's a typical graph from a day's run in that demonstration, and you can see the volume of the concentration of CO2 going into the mixer is around that 10%, and going out at the beginning of what is a batch process, you're stripping about 50% of the CO2 out of the flue gas. Over the 15-20 minutes of the batch, that reactivity is used up, so the concentration of CO2 going out of the mixer gradually increases. And the products we made from that demonstration are typical rounded lightweight aggregate that was used and demonstrated successfully in concrete blocks, which is the typical application of our aggregate. But also, because of the nature of the material, we could also investigate using it as a fertilizer. Benefits of using it as a fertilizer is that a lot of CKD or cement kiln dust in Ontario is already spread on land, but it's a very dusty material, and so it blows away. So if you granulate it and carbonate it, you reduce the alkalinity of the material. In terms of CO2 capture, that's not quite as good as using it as a building product, because obviously, unless you can argue that the CO2 is captured in the soil, the release of the CO2 occurs. So we would prefer to make building products out of our materials. So having successfully deployed our pilot plant in Ontario, in 2019, we had the opportunity to deploy it at UK cement works, funded by the government, UK government's Innovate UK funds. And this allowed us to automate and improve the control and monitoring systems within the containers. And the output of this project was the commercial ready plant that we've now deployed down to VCAT in the south of France. So this is the picture of our new plant being installed at Montpellier. It arrived in July, but of course we've been hit by the problems that are occurring the world over. So it's rather limited our access to the plant, and we are still commissioning it, and hopefully we'll be running fully early next year in January, assuming that the restrictions enable us to get back into France. So it's very difficult to play with the CO2 in the container, because obviously you're starting off with a 10% concentration of gas. But I want to emphasize that there are some advantages of capturing the flue gas directly. One of the problems with carbonation, as we do it in carbonate systems, which is very much at atmospheric temperatures and pressures, the solubility of CO2 is related to the temperature, and the principle of the process is that the CO2 will ionize in a thin film of water. So if you have too high a temperature, the CO2 solubility is reduced, so the reaction is reduced. So actually, if you can control that exotherm, you get a much better process. So this is just a couple of runs in the laboratory to compare the reaction at different CO2 concentrations. So the blue line is 100% CO2 and the orange line is 40%. And you can see how the exotherm is reduced and also delayed, so that in your full-scale plant at 10% CO2, the exotherm is very much more controlled, and we don't have so much of the problem of that heat. But if you look at the CO2 uptake of the products of this process, there's very little difference. It's a bit artificial here in it showing that the 40% uptake is slightly higher than the 100, but that's within the experimental error of the determination. So really what it's saying is that we're not affecting the CO2 uptake as long as we're delivering sufficient CO2. And in the commercial plant, that's the balance that you have to make between the flow rate of the CO2 and the problem that you might blow all the fine dust that you're trying to treat out of the mixer. So this is it's the materials handling side of the process that is the key to the success. The other thing that we found is that you can blind the grains if you're using 100% CO2. The reaction is so quick, as you can see from the exotherm there, that you get a zone of carbonate around your grains, which prevents the diffusion of grains of the CO2 into the grain. So overall, the reaction can be more efficient at lower concentrations of CO2. So just to talk about our products, the typical properties of an aggregate made from cement bypass dusts. It's lightweight, and when you test it according to the lightweight aggregate standard 13055, you get an acceptable range of properties, typical of other manufactured aggregates such as Leica or Lightag, but of course it's carbon negative. I have to emphasize though that it's not a granite, and you've made it within 15 minutes, so it can't be compared with a strong natural aggregate, and you have to think carefully about the applications, and the application in concrete blocks is one of the most appropriate for this sort of material. These sorts of residues are also high in chlorides, and so you have to be careful about their use where there's concrete with steel reinforcements. And so the other thing is that because they're manufactured from residues, and the legislation around the residues varies by state in Europe, the acceptance of them as a product is a challenge and has to be negotiated through each state. So we've also demonstrated the system at AVR in Duvin on their energy from waste plant, but this one is slightly different because Duvin are well ahead of the game and are already capturing their CO2 and purifying it. So we were using purified CO2 in this case because that's what's available. But it's nice to see that we're using the technology for different waste streams, and we are agnostic to the concentration of CO2. So the main theme I want to say is that carbon capture and utilization can be profitable. We wouldn't be doing it if we weren't generating income for both ourselves as the company, but also our clients. So our main raison d'etre is to save the CO2 generator and the waste generator or the residue generator money. It's got a huge potential to capture millions of tons of CO2 across Europe and the world. We're removing waste from landfill and generating useful materials that will replace natural aggregate and therefore the carbon footprint of those natural aggregates. The technology is proven at commercial scale. And what we're trying to roll out now is this plug and play solution that is scaled to meet the requirements of individual waste streams using the local flue gas derived CO2. Thank you very much.
Thank you, Paola, for this very interesting talk, for presenting the technology of Orbix. So as you know, you will be able to ask questions at the Q&A session at the end of the session. So now I would like to give the word to Mieke Quarreberg, a program manager at Vito, and Andy van Kouwenbergen from Orbix, who will present their presentation on their technology. So it will be a presentation with 2 speakers. May I remember the speakers to keep the time to 15 minutes so we make sure we have enough time to answer the question at the end. Thank you very much. Mieke, the floor is yours.
Okay, thank you. Okay, so my name is Mieke. I work for Vito, and today I would like to share with you some of the challenges and opportunities we kind of experienced during a demo project focusing on mineral carbonation products. I would like to start to thank all partners involved, because even though Vito was coordinating the demo project, a number of different partners were involved, which I will mention more in detail later. But I would like to thank especially the city of Ghent, because they really made it happen. I would also like to introduce Andy. Andy is a consultant working for Orbix, and he will kind of later towards this presentation share some insights with regard to commercialization of the Carpstone technology. Okay, for those of you that do not Vito, I work for Vito, and Vito is not a commercial company, but we are a research institute. Our head office is located in Belgium, and we focus on applied science. And more specifically, we develop technological innovations and policy challenges related to sustainability. About 1,000 people are actually working for Vito, and we are really an international organization with over the years many more international projects and even satellite offices in China and the Middle East. Okay, core technology today, already discussed by Paula, is mineral carbonation. And explained very simple, it's the reaction of CO₂ with basic minerals to form solid carbonates or rocks. It is actually a natural process, and geologists believe that over a million years ago, this process played an important role in reducing the CO₂ emissions in the atmosphere to levels that enabled life today. It's also interesting to see that calcium carbonate minerals are very abundant in nature, and over centuries, we've been using this type of materials as construction materials. So actually, nature kind of learned us that, yes, we can store CO₂ in rocks. And history proved that these materials can be used as high-quality construction materials. The challenge is, however, how to speed up the process and convert it to an industrial viable process. Maybe some words about Vito. How did our journey started? To be honest, we also started with research projects in the early 2000s, focusing on geological sequestration of CO₂. We studied rock, CO₂, and brine interactions, and were involved in mapping of the opportunities for Belgium. But it was interesting research. We were able to kind of set up some nice infrastructure and build up some expertise. But my colleagues were also confronted with some of the drawbacks, like the not in my backyard syndrome, and also high cost associated with geological storage of CO₂. At the same time, actually, we were very active in research projects dealing with recycling of mineral waste. So, of course, with a specific focus on construction products. So the logical next step was then to combine both research fields, and that is what we did. We started working on mineral carbonation, where the main research question was, can we use mineral carbonation to make high quality construction materials? Over the years, we were involved in a number of projects. Some of them are mentioned on this slide here. And typically we use high quality or state-of-the-art technology and infrastructure to kind of understand and develop the carbonation process. An example of this are we typically use microscopic techniques to study carbonate precipitation into construction materials. We use 3D visualization techniques such as in situ tomography to really study the progress or the reaction of fluids during the carbonation process. This was actually done together with the University of Ghent. We have a lot of experience with optimizing the environmental properties related to carbonated products, such as leaching behavior and CO₂ uptake. But a last example, I would like to mention that we are also involved in many demonstration projects, because we think this is quite important for innovative technologies to help overcome the value of debt. And one of these demonstration projects is the Stapsteen project that I will present today. This was actually a project executed in the city of Ghent, and it was actually a demonstration of the Carpstone technology. Carpstone is a mineral carbonation process. It was developed by Vito in strong collaboration with Orbix. And Orbix is actually an industrial company active in the development of innovative technologies and materials to be used in the steel industry and construction industry. One of their core activities is actually the treatment of steel slags. And during this process, a number of byproducts are produced. Mineral byproducts, and one of them is carbinox. And carbinox is actually a very specific byproduct. It's very fine-grained and has a very reactivity towards CO₂. So going back to the carbstone process then, explained very simple, carbstone process is a process to produce high-quality construction materials using both CO₂ and byproducts as input materials. So the USP of this process is that you do not need to use any traditional binder, such as cement, but instead we use CO₂ as a binder. So strength development in the materials happens by in situ precipitation of CO₂ during the process. When Orbix first started this process, actually they focused on the development of a product resembling a brick, and they focused on the use of carbinox as an input material. But clearly it's quite a flexible process. Different type of input materials can be used, and also different type of construction products can be produced. Okay, so when Orbix was busy in the product development, and they were kind of finished with a product that could be launched on the market in the Netherlands, the city of Ghent expressed their interest in also hosting a demonstration project in Belgium. The city of Ghent is quite interested in opportunities related to circular economy, and they are very ambitious when it comes to climate neutrality and innovation. So they said, yes, we are willing to host the demo project, and they invited the other partners, not mentioned yet, such as the University of Ghent and a small company responsible for the data visualization to join the consortium. Funding was obtained through Vlaanderen Circulair. And the objective of this demonstration project was not only to focus on the technical challenges, but really also consider boundary conditions such as product certification, logistics, public perception, legislation, environmental impact, that are really relevant for further employment of the technology towards an industrial scale. Therefore, the demonstration project was organized in 4 different steps, which I will explain a little bit more in detail during the next slides. So the first step was the technological innovation. Here we encountered 2 challenges. First challenge was related to the desire of the city of Ghent to use local products. So a mapping was done, identifying relevant input materials, and actually a certain type of steel slag was selected, but it was a different type of steel slag compared to the steel slag used, carbinox, or produced by Orbix called carbinox. And so some kind of innovation was needed, some tweaking of the mix design was needed to overcome that challenge. The second challenge was that a lot of experience was built up with bricks, but the city of Ghent preferred a paver as a demonstration product because they wanted to optimize the experience that the general public would have interacting with the demonstrator. So therefore, indeed, we kind of went back to the lab and the pilot plans and optimized the mix design for the different type of input material and also a different product. But it went quite well, and we were able to kind of meet all technical requirements and all environmental legislation criteria. And so this was well. So next step, of course, was also to look at the CO₂ footprint. And actually, the University of Ghent did a LCA analysis of the demonstrator. And it's interesting to know that just by this demo project, about 2 equivalent tons of CO₂ could be saved by using this carbstone paper instead of just normal concrete pavers. Okay, so even though it was clear what were the technical and the environmental characteristics during the demonstration project, we decided to go 1 step further and also looked at the relevant boundary conditions that would be in place when we would like to kind of put this product on the market and really work at industrial scale. Specifically, we looked at the boundary conditions related to product certification and standardization. And here we kind of encouraged an important bottleneck, because of course, carpstone material has a different composition compared to standard concrete pavers. They do not contain cement, so they are different. And local quality labels, but also European standards, typically consider both composition and performance criteria. So, okay, there are ways to get around it, but it would really help if we could tackle this challenge and work on the standardization of the products, either develop standards specifically for carbonated products or kind of work more towards performance-based standards. Okay, then next step was a demonstration that went quite smoothly. Here you can see a photo of the demo day. Some local politicians were invited, and you see Peter from Orbix and Lisbeth from Vito. That kind of opened the footpath. Okay, so in the end, indeed, you can see the footpath that's realized. So if you visit the city of Ghent, please go and walk over the footpath and experience the circular footpath. I've tried to make some conclusions that we can draw so far. So the demonstration project was quite successful. All technical and environmental requirements were met. And maybe one bottleneck we identified is that product certification and standardization could be adapted for mineral carbonation products. It's also important to remember that 2 tons of CO2 equivalents could be saved by using this concrete carpstone pavers compared to concrete pavers. And this was just for a footpath of 100 square meters. Okay, then I would like to give the words to Andy, who will tell more about the commercialization process of the carpstone technology.
Thank you, Mieke, for the introduction. So in Orbix at the moment, we are at the end phase with 3 industrial producers of building materials. Here we present very shortly 2 of them. So the first one is an existing concrete block and paving producer who has installed a new vibrating press in 2019. And he installed as well some climate rooms, and some of the climate rooms were closed. So we could easily adapt them to inject CO2 into these climate rooms. So here we are using Carbinox, so the stainless steel dust which is coming out of our production line as a material to carbonate. We need here a high strength. So like one of the participants was asking, it's quite easy to obtain a 20-25 Newton per square millimeter. But here pavers needs around 60, so it's much harder to get, but we succeed. And this press will be capable to produce around 100,000 cubic meter of building blocks. So we are very lucky because there is a lime kiln in the neighborhood. So the distance to do piping from the lime kiln is not so very far. And so we will have a CO2 source available close by. You can go to the next page, Mieke. So the second one is a blast furnace steel producer. Like Paula said in the beginning, they have a problem because their own landfill is becoming full, and they want to have a solution for their LD converter slags. They have more than 300,000 tons going to their own landfill at the moment, and they are urgent looking for a solution for them. So here we are looking not only at the vibrating press, but at the high pressure press. The CO2 will become from their own chimney to use and to concentrate to make it useful and to the concrete products. And here we will produce 2 different kind of products, a paver That's the first product, and the second product is an iron briquette. Why? Because they do have quite a lot of iron dust coming from their chimney, and they are willing to recycle this dust into their own kiln. So they need to make a briquette out of it. So here we will add a small part of their own slag, their own LD slag, to treat it with CO2 so that they can reuse the briquettes into their own kiln. So it's really a circular economical case here, where they will use and their CO2 and their own slags and make even products for themselves. In both cases, we were very lucky to have a CO2 source nearby, because this is the biggest problem that we have at the moment. We do have a lot of people from the construction materials who are asking us to develop or to make a case study of their products. But the availability of a nearby CO2 source is in most cases the element who is blocking the upscale of the system. So we really need to have a kind of subsidizing system for piping, or to push the product, the concrete product producer to move to a new site close by a CO2 source that is available. Also, we at the beginning, we started with quite a high CO2 percentage into the climate rooms. Today, we are capable to go lower and lower and lower. And so if the CO2 source is close by, we will be competitive against the cement use. If it is far away, it's hard if you have to liquefy it and then to transport the material. It's okay, Mika? So we thank you for your to be present. If you have questions, you can always ask to Mika or myself to discuss further the possibilities. Thank you.
Thank you very much, Andy. Thank you very much, Mika. So we'll take the question at the end, as said before. So now I would like to give the word to Chris Takigawa from Mitsubishi Corporation. Chris, the floor is yours.
Hi, thank you. Thank you for this opportunity. This is Chris Takigawa. I think I'm looking at the last slide. Maybe you can start from the beginning, Stefan. Yes. So I am a member of the CCUS task force inside Mitsubishi Corporation. We're often mistaken by Mitsubishi Heavy Industries, Mitsubishi Power, or other Mitsubishi companies, but we are an independent company called Mitsubishi Corporation, which we focus on trading and investments in almost every commodity. And today I would like to talk about a little bit about our CCUS activities, especially about in the concrete industry, where we believe that by combining multiple technology or companies, we can achieve net zero in the future. So next slide, please. So just a few numbers of Mitsubishi Corporation. The head office is in Japan, but we have over 90 offices in over 90 countries, covering 10 groups in total, 1,700 group companies, 6,000 employees just in Mitsubishi Corporation, and including our subsidiaries, more than 80,000 employees, and a net income of $5 billion US. Okay, so next slide, please. So just a history about Mitsubishi. So one of the oldest companies in the Mitsubishi group. We started as a trading company, and eventually we started to also do investments and business development for our investments as well, in order to expand our business. And some recent investments that we made is investment to a mapping company called HERE, or investments to the renewable energy company Eneco, both in the Netherlands. Okay, next slide, please. So again, there's 10 groups in total. We cover almost every industry in the world. You can see we cover from the natural gas all the way down to the urban development. We often call ourselves a business that we do from ramen to missiles or airplanes. In terms of the CCUS task force, because we understand CCU is such a diverse industry, meaning there's many type of sources of CO2 technology to convert that into multiple applications such as concrete or fuel and chemicals, which is not the focus today. So understanding that the CCUS work is not just done in one group in Mitsubishi, but it's more of a joint task force, as you can see in the red square here. So the natural gas group, mineral resource group, which invests in mines or LNG assets, they're the emitters of CO2. Whereas the industrial material groups or the petrochemical groups, these are the people who are the groups that are focused more on trading investment on the application side, where we can convert the CO2 in the future. Okay, so next slide, please. So just talking quickly about Japan, our Prime Minister announced net zero. Next slide, please. And also what's worth to mention is that in his announcement that he said that he'll focus on hydrogen and CCU. So we also now have a CCU dedicated roadmap. We call carbon recycling rather than CCU in Japan. There's a roadmap in the government, and there's a tremendous support to the public companies to actually grow the CCU from Japan. Okay, next slide, please. So just again expressing that because we understand CCU is a very diverse industry, from the emission to capturing separation technology to all these applications, we just want to express again that because we cover every industry from the 10 groups, we have the network with all of these areas within the CCU value chain. And so our focus is not just to focus on specific technology, but actually investing or doing business development in all of these applications in order to connect the value chain of the whole CCUS business. Okay, next slide, please. So talking a bit about our several specific projects. So one of the projects is that we received a government grant to do an R&D for producing clothing material from CO2. When I say clothing material, I'm talking about paraxylene, which is the raw material for polyester. Obviously, the material is used for PET bottles or clothing. Both has huge demand and growing demand in the future. These are both now produced from crude oil, emitting a lot of CO2. But now we're working together with Nippon Steel, largest steel company in Japan, Chiyoda Corporation, one of the largest engineering in Japan, Hi-Chem chemical company, Nippon Steel Engineering, and Toyoma University, who is the key holder of the catalyst. We will eventually produce paraxylene from CO2 and green hydrogen and be able to sell the product, a green paraxylene product, to produce a completely CO2-free clothing or PET bottle in the future. Okay, next slide, please. So the main topic for today, CO2 to concrete. So again, we're not just focused on one technology or company, but we understand that the industry is very diverse, very segmented. We understand the need to combine multiple technology to actually solve the larger problem. So we separated the industry into four, basically the ready mix side, the precast side, and also the ways to reduce the CO2, which is the replacement of cement, and also to mineralize the concrete or to produce aggregates from CO2. So in terms of the precast technology, I will touch on details later, but there is a technology called CO2 Suicom in Japan, which we have exclusivity license and new technology development. We're also partnership with Blue Planet and OCO, both probably a very famous companies everybody here will know about. We're also looking into other technologies and companies in the ready mix side, and not just limited here, but other technologies in order to actually maximize the reduction or removal volume of CO2. Okay, next slide, please. So a bit detail of the specific technology. So CO2 Suicom is not a company, it's a technology developed by 4 Japanese companies 10 years ago. Kajima Corporation, which is one of the largest construction companies, Energia, one of the largest energy companies in Japan. Denka is a chemical company, and Landis is a precast concrete manufacturer. The technology is, from our knowledge, is the only world commercial carbon negative concrete. It utilizes a admixture called gamma C2S, which you can see on the left side, which will replace the cement to reduce this emission from cement and also accelerate the carbonation process of the whole concrete. We will then put that mixture into a curing chamber and capture CO2 into the concrete itself. So the graph in the middle shows the total reduction volume. The 197 red kilogram per cubic meter is the reduced volume by replacing the cement with the additive, whereas the 109 kilograms is the captured CO2 during the curing process of this of the concrete chamber. So by combining that, this will exceed amount of total emission from a normal cubic meter of concrete, which is why we call it a carbon negative concrete. The technology is already used in Japan. The images below on the right side are all images in Japan already utilized, already used in one of the largest highways in Japan as well. The only restrictions here is that it's a technology only for precast concrete and non-reinforced concrete. And it's also a very high cost technology. So we're looking forward for business schemes that we can actually enable the product to launch. Next slide, please. So understanding that limit of the CECOM technology, we also received a grant to further develop the technology to expand the technology for reinforced concrete and also to the ready-mix side as well. So in the future, we believe that by utilizing the similar technology, we'll be able to reduce carbon negative for the whole industry for concrete. Okay, next slide, please. Okay, in terms of our partnership with OCO Technology, so I believe most of the people here will know about the company. The company is one of the leading companies to utilize waste materials such as APCR from biomass fly ash, carbonate and aggregate it into lightweight aggregates. Whereas our partnership is more focused on new technology development together with OCO, Mitsubishi, and a Japanese engineering firm. The agreement is to develop new technology to utilize steel slag or other materials rather than APCR, and utilizing OCO technology to produce the same product, which is lightweight aggregates or normal weight aggregates. We believe this will expand and open up the OCO opportunity to utilize different waste materials and to capture more CO2 in these type of new waste. Okay, next slide, please. Another area is a partnership with Blue Planet. This involves financial support to the company to actually support the feasibility project in California. We're also working with an engineering company together in order to create what we call an engineering package in order to license the technology to other companies. So, and the difference between OCO and Blue Planet is sorry, I haven't mentioned this, but the material for the waste is different. So OCO utilizes APCR, whereas Blue Planet uses demolished concrete or returned concrete, which is a different material. And also the process itself is different as well. So a lot of questions we are often given is that why focusing on two aggregate companies? Although there are both products of aggregates, both are very different process and utilizing the different materials. Okay, next slide, please. And lastly, so carbon credits is one of our main focus as well. So we understand most of these technologies or companies are struggling to actually create a business, an actual business because of the high cost of all this new technology. We believe that the voluntary carbon market is one of the greatest opportunities. We just joined the task force on scaling voluntary carbon market, which is led by Mark Carney. So this will be one of the large opportunities for us to understand how the market is created and how we can create value in order to boost, insert these new type of technologies into the task force. In that task force and in the voluntary carbon markets, we also are planning to develop carbon removal credits, which is a bit different from the normal credits that's created from like forestry or renewable energy, which is traded now in very high value. So CO2 CECOM or OCO technologies are samples of the technologies that we're working together on to create carbon removal credits. We're working with a company called South Pole, which is a Switzerland carbon credit carbon credit developer and broker, in order to create a carbon removal credit platform in order to connect the buyers of the carbon removal credits and the suppliers of these credits, which will be CO2 SIGAM or OC or any other technology that could create removal credits by reducing CO2. Okay. And sorry, yeah, one more last slide. So just showing our partnership with multiple companies, we just want to show that because we are not a technology company or engineering company, but more of a trading and investment and business development focused company, we work together with a lot of companies in order to achieve the net zero commitments of Japan. You can see we're also working very closely to like the Team Expo, one of the largest events in the world, which is planned in 2025 in Japan. COP26, obviously, Toyota Woven City, so on. And yes, that's pretty much from myself. I'm happy to answer more questions, and please contact. This is my email, my company email, to further discuss our opportunities. Yeah, thank you very much.
Thank you, Chris, for this very interesting presentation. This closes the session on technical development. So before we go to the questions, now we give the floor to Professor André Bardot from the ETH in Switzerland, who will speak about CO2 mineralization and the climate mitigation role of CO2 mineralization from a life cycle analysis perspective. André, the floor is yours.
Thank you. Can you see my screen?
Yes, we can.
Okay, yeah, thank you very much for organizing the event and all you for joining. I'm happy to present some work we did on life cycle assessment for these processes. It has been touched upon and it's a strong motivation to do this. And so we looked into what are the environmental impacts of actually doing carbon capture and utilization. And the programs had only my name, but I want to emphasize that the work you'll be seeing is mostly been done by Hessam Ostovari, so we should give him the credit to him. Now, the exciting thing about CO2 by mineralization is, for me as an academic, it's maybe thermodynamics, because usually how do we come about CO2 is the starting point is usually that we are using still too many fossil fuels to generate energy, and the end product is CO2, which is then low in energy. And many of the products we've also seen in the previous talk, they need additional energy in order to be transformed into methanol or methane or another product. But this is not true for mineralization because the products of mineralization are actually lower in energy. So the reactions we are looking at, we have been discussing, are basically the conversion of some metal oxides with CO2 to carbonates. And the good news is that this goes thermodynamically downhill. So we're actually having an exothermic reaction, and we're generating something that is more stable than CO2. So we're having intrinsically the carbon capture and storage idea, or in particular, the storage idea. But what we've seen in the previous talks, that mineralization can not only store CO2, but actually what we create are value-added products. And this is then an additional benefit that we are seeing. So this is exciting. And that's why we looked at different routes, and the feedstocks we have been analyzing are mostly minerals or waste as starting points. Now the thermodynamics looks all exciting. There is obviously a problem, and that's how also been touched about. That is that the kinetics of these processes are often too slow. If you start on natural materials in particular. It occurs, but it occurs on very long time scales. Now, this can be overcome. So we know a lot of tricks, and the companies we've been hearing know tricks to accelerate mineralization to get this in reasonable and technical time scales. But these tricks then also need energy inputs that generate CO2. So in principle, CO2 mineralization looks great, but the question is, does it overall, with the tricks we need to employ, generate environmental benefits? And that's what we looked at. So what we did, we employed life cycle assessment. That is, you do the mass and energy balances through the life cycle from the extraction of the products, the production process, its use phase, recycling, and the end of life. And then you look at different environmental impacts. I will focus mostly on CO2, but I will also highlight that we should not forget to look at other environmental impacts. So with life cycle assessment, we get a very holistic view on the environmental impacts of a process, because we look through the whole life cycle and through different environmental impacts. And so we looked at different technologies to get a feeling about what are the important life cycle stages and what are the critical elements of deploying CO2 utilization. And the scenario I want to show you is starting from a world where we have a CO2 emitter, which is taken here as a steel plant, and we want to use the utilization, final utilization is in a cement plant. So currently these two operations run independently. What's now the idea of inserting CO2 utilization by mineralization here? So what we could do, we could take the CO2, capture it at the cement plant, give it to the CO2 mineralization plant, which is generating products. And these products, as has been discussed by the previous speakers, can be used then as cement additives and then save emissions at the cement plant, because we need to produce less virgin cement. So what you already see, there are basic two elements, two benefits that we have. That is, we save on the emissions, and we save from the steel production, and we save on the production at the cement plant. So if you do the math, what we can calculate is basically we can look at the savings that we get. That is, we look at the CO2 mineralization process and subtract the world that we had before. And the results you're going to be seeing are the differences between these two worlds. So it's basically the sum of how much do we save at the cement plant, at the steel plant, and how much do we save at the cement plant. Why am I showing this graph in such detail? What's important is the numbers that you're going to be seeing are the results of these two worlds, which means if I show a negative number, it does not mean that it's overall carbon negative to the climate, but it means that I save compared to the status quo. So any negative number means it's better to do this. If it's positive, it means that we are actually overall emitting more CO2. That's important to have a clear understanding what's carbon negative and what is only carbon reducing. Okay, so we looked at the life cycle stages of CO2 by mineralization. So the heart of it is a carbonation step, but we need to go upstream. So you have to balance the feedstock supply. It's pre-treatment. There's a second feedstock, which is our CO2, which we take in this example from the steel plant. We need to capture it. They meet in the carbonation reactor. And afterwards, in order to convert it in a product, we usually do have some kind of post-processing. And then we have our useful product, which in this example is in the cement use. So in order to compare different technologies, we looked at the storage. So in our product, we will be storing 1 ton of CO2. And to be more specific, we looked at a number of processes from the literature using different kinds of feedstocks, different types of reactor technologies, different concepts. And here is an example based on serpentine. And basically, you fill up all the process steps. So the feedstock supply, all the mining, crushing, you calculate, collect the data. You have the pre-treatment step. In this case, this involves a heat treatment. And then we do have the carbonation reactor, all the handling of the recycle streams. And finally, we end up with our cement additive in the use phase. So we collected all this data. What's important, what is the data based on? So this is for the CO2 mineralization processes, we used as much as we could, and this is all actual experimental data, but on the lab scale. For the background, in particular energy supply, we use data from the literature. We used data from the literature, but what is important, we use the energy supply from today. So this is about basically what we have achieved in the lab using today's energy mix. So how does it end up? So this is the carbon footprint in detail for the serpentine process based on a DOE study. So we do add up the carbon footprint per CO2 stored. I said it should be carbon negative compared to today. Otherwise, we shouldn't do this. So how do these numbers add up? And we have an upper bound, which corresponds to the CCS limit I will discuss in a minute. So first, we are emitting CO2 to produce our feedstock. For the pre-treatment, we generate, because of the energy supplies of the materials we're using, we are emitting CO2. But then we defined we will be storing 1 ton of CO2, which is no longer emitted at the steel plant. But for that also we needed energy in order to capture the CO2 and compress it. We need energy to run the carbonation reaction and the post-processing step. But then we give an additional credit because we are now we're not only capturing, but we are utilizing our CO2 to replace cement. And this replaces virgin cement, so we get a substitution credit. The factory needs some amount, but the good news is that overall, we are reducing the CO2 emissions by CO2 by mineralization based on achieved rates in the lab, based on the current energy mix. And this is really exciting. And what you see is also in this graph is the benefit of not only storing CO2, but also utilizing CO2 to replace current products. By this way, we can exceed the CO2 reduction that even a perfect carbon capture and storage process where we just store the CO2 would reach of -1 ton per ton. So we can go beyond this because we're combining these two effects. So the important message is mineralization can really reduce the CO2 footprint, and we are not only economically, as been mentioning, but we are really getting the two benefits from not only the storing, but we can even be better than storing by utilization. This is not only true for the one process I've been showing you. We looked at a number of processes based on different pathways, either using direct mineralization as shown in the previous example, or indirect mineralization where we first leached out the magnesium to produce the carbonates. So this is a process I've been showing to you, and maybe just look at the yellow bars. And if you look at the different pathways we've been analyzing, what you see is the yellow bars, they are always negative for all processes we've been looking at. And very many of them, even in the today's scenario, are beyond this limit imposed by CCS. If you see where does the benefit really come from, it's important to get the substitution credit, which is shown in orange here. And the downsides come then from energy intensive processing steps that are still have strong impacts based on today's energy demand. So we do have this trade-off between the energy demand in the process and how much do we gain in the products. But overall, there's good news. So these pathways reduce the carbon footprint. They can even reduce it a lot. And the key is really, and that's why I'm excited to see the companies in the previous presentation, because the key is really to get the substitution credit that is we make useful products. So we were really excited, and this work has been published, and through this excitement, Hassam called this, what we're doing here is rocket use of CO2. How can we push this use idea further? Is by really, because a utilization concept we looked at was in a cement plant. The next step, natural step, would to say to capture also the CO2 at the cement plant. So what we could do, cement plants are emitting CO2. Let's capture this CO2 and run the CO2 mineralization. You could do this in the classical, I would say, just to store the CO2, or what has been shown in the literature that in particular, these minerals usually also contain silicon, and the silicon oxides, they do have cementitious properties, but they are pozzolanic. So you could use them to produce blended cement. And this has been demonstrated in the literature, and I will show you that this is then this combined CO2 mineralization and cement production concept is very interesting. Also from the environmental viewpoint. So what's the idea? So what is the benefit then? So now we assume that we capture at the cement plant and we produce blended cement that contains 80% regular ordinary Portland cement and 20% of our filled material. So what is then the overall carbon balance? So if you compare it to regular cement, we reduce the amount of regular cement because we are using 20% of our mineralization products. We store the CO2. Now there is a price we have to pay, the price you already know, that is the energy demands and the CO2, resulting CO2 emissions from the mineralization process. But overall, again, in a scenario for today, you could reduce the carbon footprint by 40% by combining CO2 mineralization into a cement plant using today's state-of-the-art technologies. If you want to go even further than 40%, you should switch your energy supply to a low carbon energy mix. And the key is really to work on the blended fraction, how much CO2 utilization products, how much carbonates, how much silicon oxides can you integrate into the cement that it's still cement in the end. And obviously there's also room for improvement in the mineralization processes. So this results show the promise of CO2 utilization for the from the CO2 footprint point of view, but I want to point out that there are some trade-offs. So I've shown you get the CO2 down, but if we employ this based on today's energy mixes, we should be aware that we're actually using more fossil energy. We are also using more metals because our feedstocks, the feedstocks we are looking at were natural feedstocks. So this would go up. You could benefit by switching to renewable energy. This would help, I discussed this before, in the CO2 footprint. This would also help in the amount of fossil we are using. This would not help with the virgin materials. So one point I wanted to leave you with is please be not only concerned about the CO2, but look also at other environmental trade-offs. Obviously, a greener electricity will already help, but we also should look at the whole consequences of the new supply chains we are building. So with this, I want to conclude and point out again that CO2 by mineralization can reduce the carbon footprint already today. I think a main point is that the key in our understanding is really to develop the products that are useful, because a substitution credit is really important in the carbon footprint that we are seeing. So it's exciting that there are more users and more products being developed at this point. Thank you very much.
Thank you, Andre, for this very encouraging and interesting talk. I think we saw today the role mineralization could play to decrease the carbon footprint, and we saw also that the technology are there. So now the last bit we need to discuss is what do we need to get mineralization upscaled, and this is a favorable legislative framework. And I let the word to Stefan Gillis, our EU Affair Manager, who will speak about this, and then we will go to the Q&A.
Thank you very much, Celia. You should all now be able to see my screen, and also from my side, I want to thank you all for your participation here today at this workshop. So as Celia said, my name is Stefan Gillis. I am EU Affairs Manager at CO₂ Value Europe. And in a couple of slides, I will explain some of the contributions of mineralization specifically to European objectives, but also how a policy and regulatory framework should still increase the marketization and uptake of mineralized products so that these can effectively contribute to climate change mitigation. So if we go to the next slide, so today we have been talking about CO₂ mineralization. So CCU covers a large set of innovative processes that can recycle CO₂ into a variety of valuable products, such as chemical building blocks, synthetic fuels. But what we have been talking about today are indeed also the building materials. And in essence, CCU is circular economy applied to carbon as well. So what we have seen in presentations here today is that CO₂ can thus not only be considered as waste, but also as a resource. Because indeed, a major part of our economy is based on indispensable carbon containing in products. And in the future, such products can be manufactured also by using sustainable source of carbon. So when you, for example, capture CO₂ from the air, you get negative emission through mineralization. That CO₂ that is sequestrated is moreover captured into a permanent and stable manner while as said, the reaction itself in theory does not require much additional energy inputs. So all of these contributions and these benefits do effectively contribute to many of the EU Green Deal objectives that have been stated and that have been worked out over the past months. So we have seen in several presentations this morning that in principle technology is ready to be deployed, and we have also seen the benefits of how mineralization can contribute to climate mitigation. Still, mineralization needs to get a correct recognition as a permanent CO2 sequestration method. So within our association, within CO2 Value Europe, we are heavily working towards this recognition. What we believe is that, for example, mechanisms boosting market demand for these CO2-based products, these should be implemented, and such mechanisms could then include public procurement targets, auctions, green labeling, etc. On the other hand, a regulatory framework that favors the permanent sequestration of CO2 into these construction products, that needs to be developed. And such framework could include, for example, state aid guidelines. CCU technologies could be introduced into the scope of the guidelines on state aid for environmental protection and energy. Sustainable finance has a key role to play in reaching Green Deal objectives. The Commission is currently establishing a list of actual environmentally sustainable activities by defining technical screening criteria for each of these environmental objectives. But currently no technical screening criteria for the utilization of CO2 have been developed. But CVE is heavily advocating for these CCU technologies to be included, so that also CCU can benefit from sustainable finance. Another example is carbon removal certification. The Commission is currently tasked to come up with a proposal for such a mechanism by 2023. And we as CO2 Value Europe are very much also looking forward to see how carbon removals will be supported, and we're also very much looking forward to cooperating with the European Commission to set up a scheme that would be able to appropriately support CCU mineralization as such. And then as a last point, I want to mention the EU emission trading scheme. This is currently under review, and we believe it is key important that the value of mineralized products in terms of capability of CO2 sequestration is recognized through the ETS. Indeed, as was already a couple of times said and clarified, CO2 is, through mineralization, is stored permanently and in a stable manner. Currently, one example of mineralization, PCC, precipitated calcium carbonate, is recognized by the ETS as a non-emission. So this means that the operator of an ETS installation can subtract CO2 in case CO2 is transferred out of the installation and used to produce PCC, in which used CO2 is chemically bound. We as an association very much believe that mineralization technologies as such should get a similar recognition because of the fact that CO2 in these technologies are similarly chemically bound in a permanent and stable manner. And with that, I want to thank you very much for your participation again, and I hereby hand over the floor to our Secretary General, Anastasios Perimelis.
Thank you very much, Stefan. Thank you to all of the speakers. We are a little bit beyond time, but it has been a very useful session until now, and I would like to take some more time than originally planned, if there are no objections to that from our panelists, to ask a couple of questions. The ones that we cannot answer today, we will gather them and we will answer them together with the presentations that will be shared later on. I would like to ask, I would like to start, there have been a lot of questions on the quality of the CO2 stream. So I would like to ask all speakers, Mike and Andy and Chris. Paula will join again in a while. What are the impacts of the CO2 purity or on the final material? Are there any critical components that should be avoided? And what happens with the existing impurities in the CO2 stream after the mineralization process? Mike or Andy, would you be able?
I will just answer some of the questions, and then Andy can take it from there. So at lab scale, we indeed looked a lot at the purity of the CO2 and the impact of that on the carbonation process. What we observed was that, yes, you can really work with lower grade CO2 concentrations. I think we went down to 20% in the lab. Then the input was that the process becomes slower. So the kinetics are a little bit slower. So you require more time for the carbonation to happen, but actually the total carbonation degree remains the same. So it is indeed possible to use kind of diluted streams of CO2 also for the carbonation process. That's actually what Orbix already has been doing on a pilot scale as well, I think, Andy, but maybe you can comment.
So what I can add is that in the beginning, but then I'm talking about 15 years ago, we started with pure CO2, and today we are looking even below 40% of CO2 into the concentration. We are willing to go up to the concentration like they are available in most chimneys, because most chimneys you only have about 15, maximum 20% of CO2. So it takes time, but we are learning, and most of the projects we are doing at the moment is 40–45% of CO2, but we are going down and we are proceeding. So if you are looking at other elements like sulfur and other particles who can be into a chimney, at the moment we are not seeing any effect of them into the carbonation. So so it's an ongoing process, and we will succeed for sure into the future to go down into CO2 concentrations as well.
Okay, thank you. And there have been some questions on the standard operating conditions, on temperature, on pressure, whether there's a need for humidity or any kind of solvent use. Could you elaborate on that a bit? Are there any particular operating conditions that are needed?
Yeah, well, as I explained already before, carbonation process is quite a flexible process. And so the operating conditions really depend on the quality of the end product. So for standard products, as Andy explained, you don't need elevated pressure. The process works at atmospheric pressure. Yeah, of course, when we also managed to really produce quite high strength materials, and there we observed that we needed elevated pressures. So actually the pressure is really dependent on the quality of the end product you need, at least for the carbonation process. And when it comes to other factors like temperature, also that depends a bit. We noticed that by elevated temperature, you can kind of control the environmental quality of the end product. So it also depends a little bit on the input material you use. But of course, you don't need elevated temperatures like Paula showed. It's an exothermic reaction. So even if you don't use elevated temperature, the temperature inside the curing chamber will rise up to about often more than 60 degrees, often 70 degrees. And that will kind of help as well in the environmental properties. Please, Andy, continue.
Yeah. The only element that I wanted to add, it like Mika said, it depends on the demands of characteristics like strength at the end of the end product. But it depends as well on the materials used, because we do have projects where they want really to use 100% of slags, where the driver is more to get rid of the slags and to find a solution for the slags. But we have other customers or projects where they are willing only to replace the cement with a certain small percentage of slag, and to use as much as possible a local granulates, local sand. And this has as well a big influence on the total system. So for each customer, you have to find out, and it takes some time to find the best mix of CO2 of ingredients of your mix.
And would this affect, Andy, let's say a large-scale constant production of a certain product, the specificities and the composition of the input stream, for example? Would it be, let's say, an obstacle when we go to larger scale production?
At the moment, we are not seeing this as a real obstacle to go to the largest scale. The biggest obstacle, like I've said into the presentation, is to have a CO2 source who is available, and CO2 source who suits the mix, and or the producer who is willing to delocalize to the CO2 source. These are the two main obstacles. So in most cases, we are finding a solution, but the biggest obstacles is the availability of the CO2 source.
Okay. Chris, I had a question for you. Where does the gamma calcium oxide and silicon oxide come from? Was the question, and whether there is a significant cost increase of the carbon negative concrete towards compared to the standard concrete.
Sure, thank you for the question. In terms of the gamma C2S, so currently the gamma C2S is produced by byproduct calcium hydroxides. These are byproducts from normally acetylene plants. So where if there's any production of acetylene, there will always be byproducts of calcium hydroxide that we can utilize in order to produce the gamma C2S. The calcium hydroxide cannot be cannot be produced by other materials since that will emit CO2 anyway, CO2 itself. So we will rather use byproducts, which will reduce the emission from that product. The second question was the strength of the cost. Yeah. Sorry, in terms of the cost of the concrete, so it really depends on the precast concrete that you would like to develop. So if it's a thinner product, obviously it will be a faster curing time that will lower the cost. So currently we produce panels, which is around 1.1 times the cost of a normal concrete, so relatively low cost. Whereas if you would like to produce a rather larger concrete block, that might be 2 times higher expense than normal concrete. So it really depends on which final product you want to produce. And it also really depends on how much CO2 you want to reduce, because these are cases of achieving carbon negative. So if you're not, if you would say we just want to reduce 50% of the CO2 reduction, that's a total different question. Obviously, that will affect the cost in a good way. Yeah.
Thank you, Andre. There were some questions. You responded to one online, but maybe it's for all attendees to hear. How is the potential substitution degree of the CO2-based material taken into consideration when comparing with the conventional material?
Yes, yeah, this is a very important question. That's why I also emphasized in the end, the product quality is really decisive. Yeah? So what the question is, are you still producing cement if you mix it, or what are you producing? What's the product? So what in the calculation I have been showing, we took into account a substitution factor. So basically, there have been reports, people analyzed the performance of this kind of blended cement where the silicon oxides are blended, and we've seen a loss in performance. And we took this, so it's not a one-to-one substitution, but we downscaled this by the factor reported in the literature. But this is really the kind of data we need. And you really need to make sure, as has been discussed, these standards are kind of tricky, but at least you should meet the performance standards to make sure that what you are producing is still cement, and whether you can, what kind of factor. So it's not a one-to-one usually.
And you already made this distinction, and it is very helpful. There were some questions about what does it mean carbon negative, but you already made the clarification that it's compared to the product, the conventional product, and not from a climate perspective necessarily going to negative emissions, which can still be achieved through mineralization, but from while removing the CO2 from the air, for example, and not from point sources. So just to clarify this terminology, because sometimes it is used slash abused sometimes. So yeah, there have been, and I will close with this question before closing the entire webinar, is there have been some questions on the importance of the definition of the product end of waste for the final product. And would you have a comment there, maybe Mike or Andy, from a product specific, from the downstream side? Is there something on the definitions of end of waste or product that need to be considered to accommodate CO2-based products?
Yeah, actually, for the capstone process, at the moment we've been using focusing more on byproducts, not at waste products. So it means that this is really not a waste starting with. So you end, you turn up not as you still have a useful product at the end. But of course, when we look at a end of waste criteria, it's clear that every region has its own criteria. And at the moment, there is not a European kind of norm or legislation dealing with end of waste criteria. So of course, I would imagine that it would really help to kind of further develop the technologies across Europe, because now you kind of need to look at the legislation that is there in each region, in each country, and that is, of course, makes implementation more complex. Yeah. Okay.
We're a bit past our normal time plan, and I would like to stop the Q&A session here. We have thank you very much to all the speakers. Thank you very much to all the attendees. Before closing in a standard way, we would like to leave you with a video from our friends at CO2 Value Australia. And with this video, you will have heard of 3 continents explaining advancements in mineralization, which shows the global impact of CCU processes, and in this case, mineralization. Thank you all for attending. Stay for 3 minutes more to check the video. Wish you all a safe end in 2020, and spend as much time as you can with as many family members as you are allowed to. during the Christmas time. Merry Christmas, and let's hope that 2021 would be a healthier year and a better year overall. So I'm going to share my screen with a video, and thank you very much for your attendance.
I do not hear the sound. Did you share the system sound?
I have to share the sound.
Perhaps I can share the video.
Yeah, Stefan, go ahead. I think I have an issue.
No problem at all.
Hello to all of you mineralisation enthusiasts out there. I'm Sophia Hamblin Wong, and I'm the COO of Mineral Carbonation International, or MCI, as well as the co-founding director of CO₂ Value Australia. At MCI, we have a global reference pilot plant in Newcastle, Australia, which every day is turning CO₂ into building materials like cements and concretes, plasterboards, as well as industrial products and everyday products. In Australia, we have choked through one of the worst bushfire seasons in living memory. We know that catastrophic climate events will continue to be more frequent and have been predicted for decades. And it's because we have been using our atmosphere like an open sewer, and that has to stop. It's not all doom and gloom, though. We need to reduce, reuse, recycle, and remove carbon dioxide, and now even the G20 agrees with us. They have defined a circular carbon economy platform. Minerals, rocks, and wastes are incredible places to store CO₂, don't you think? Especially when you can turn those materials into value. The message has really been connecting as well, with MCI and mineralisation technologies being featured at the World Economic Forum's annual meeting in Davos, at the UN Climate Action Summit, in the New York Times, as well as in a social media post by the WEF that has reached more than 200,000 views at last count. Now more than 50% of the world's GDP has signed up to net zero by 2050. It's now a race to zero. Good quality carbon offsets and the technologies that enable the transition to net zero are now sprinting towards a cleaner future. We know, however, that the health of our technologies depends on the health of the overall innovation ecosystem. We still have a bit of work to do globally to educate and advocate the public and policymakers about the potential impacts of CCU. We need to bring the public along for the ride with us. CO₂ Value Australia this year has ensured that the Carbon Capture and Use Technology Group was listed as an emerging technology in the Low Emissions Technology Investment Roadmap, as well as facilitating the launch of the CSIRO's commoditisation of CO₂ roadmap. If any members of CO₂ Value Europe or other global members have operations in Australia, I strongly recommend you get in touch with us so that we can ensure that we're advocating in Australia for the entire CCU industry. CCU and mineralisation is gaining momentum in the public's eye and with policymakers globally. Let's work together to ensure that we accelerate our technologies, create new industries and good jobs, and most importantly, reach our Paris climate goals.